What do you think of when you hear the term gravitational waves? To me, I imagine some sort of intergalactic beach existing out in the middle of space where pompadoured astronauts surf while groovy music plays in the background. As you can probably guess, that's nowhere near what scientists define them as. Luckily for us, though, the actual definition is arguably more ridiculous and extreme. I'm getting a bit ahead of myself, though. We first have to cover some basics for any of this to make sense. While I assume you're all familiar with the basics of classical physics, let's do a quick review to make sure we're all on the same page. Newton is most famous for his laws of motion and how they apply to stuff here on Earth, but he also had some theories that explain how gravity works. Put simply, any object has a gravitational field that extends out from it in every direction. The force exerted by that field is based on the mass of involved parties and inversely based on the distance between them. This is all summed up in Newton's law of universal gravitation, which can be further modified to calculate other values, like velocity, mass, or distance between orbiting objects. These formulas are all still used today because they work great at predicting the behavior of heavenly bodies. Now, a sane person would call it good enough and stop there. But scientists are relentless in their pursuits of knowledge. Sometimes that drive leads them to opening doors that should never have been opened. Case in point, this. You unlock this door with the key of imagination. Beyond it is a dimension where a meter does not equal a meter. A second is no longer a second, and a straight line is not straight. You've just crossed over into the relativity zone. To answer what all that was about, let me first present you with two physics concepts: the propagation of light in a vacuum and the principle of relativity. The former states that all light travels at roughly 300 million meters per second, while the latter posits that laws of nature should perform the same regardless of your frame of reference. Each of these laws have decades of evidence supporting their existence, but when you put the two of them together, you get some weird results. For example, if you're sitting in a train car that's traveling forward at 30 meters per second and someone on the side of the track shines a flashlight in the same direction you're heading, from his perspective, the light is going at the speed we all agree it should be, but from your perspective, it's going at 30 meters per second less than that. That might seem like a minor difference to you, but this dissonance fundamentally breaks a lot of physics. Physicists tried for a long time to solve this problem with middling success until Einstein published his theories of special and general relativity. How he actually solved the problem is a story for another time. If you're curious, go read his book on the topic. While it isn't exactly Sunday afternoon reading, it does a better job explaining it than I ever could. Anyway, reconciling these two incompatible truths also created a whole host of new, wacky phenomenon. Fortunately for us, an understanding of gravitational waves only requires that we know three things about relativity. Firstly, the effects of these theories only come into play when you are extremely massive or are moving ridiculously fast. In other words, all your Newtonian formulas still hold up in almost all situations. Secondly, the universe we live in is a four-dimensional one. That sounds scary, but basically, any point in our universe has an x, y, and z coordinate as well as a time measurement. The third and final thing to understand here is that gravitational fields stretch and bend the fabric of space-time. The larger the mass, or the faster it's going, the bigger the distortion. This means that, when placed in the vicinity of a substantial gravitational field, clocks will tick slower and rulers will be longer in comparison to their typical behavior. Okay, I know that was a lot to take in, but I promise it gets lighter from this point on. We now finally have all the basic knowledge we need to talk about the meat of this presentation. So I ask again, what are gravitational waves? Basically, they are moving examples of the space-time bending effects detailed in general relativity. When a wave is produced, it steals some of the gravitational energy from its source and flies out into the universe at the speed of light, subtly affecting everything it passes through on its journey. Putting aside the mind-boggling physics of these phenomenon, they behave the same as the mechanical waves you're familiar with. They have peaks, troughs, frequencies, and can produce interference with one another. Additionally, just like any wave that carries energy, as it spreads over an increasingly large area, the force it carries gets weaker. Gravitational waves are sorted based on what their source is. Technically, every object in the universe produces waves, but we don't talk about them because the effects are so small that they're negligible. When scientists discuss this topic, they're almost always talking about the effects that are produced by only the largest and densest of stars, or black holes. Of the waves that actually matter, we have 4-ish categories to choose from, but I'm only going to mention the compact binary and spiral waves, since they're the most interesting. These guys are produced by two massive objects orbiting one another. The frequency of these waves increases over time because they steal gravitational energy from the orbit, which results in the objects getting closer and faster. This in turn makes subsequent waves stronger, and repeats the whole process until both objects collide. Scientists have identified 3 separate sources of these waves, namely a 2 black hole combo, a 2 neutron star combo, and a neutron star black hole combo. Each of these scenarios produce slight variations in frequency. Let me show you what I mean. This is the sound of 2 black holes merging. Did you get that? Here, I'll play it again, but modified to make it more audible. Now, here's the sound of 2 neutron stars merging. Not exactly riveting, right? What if I told you that that first clip was produced by 2 black holes, each over 25 times bigger than the mass of our sun, moving at half the speed of light? Still underwhelming? Yeah, I get it. But for the scientific community, those sound bites represented the results of a decade-long struggle, and physicists all over the world went wild when they were released. So why were scientists so thrilled by those audio clips? Let me tell you a bit about the history of gravitational wave detection to explain. Einstein first hypothesized they existed way back in the early 20th century when he released his theories of relativity. The math checked out, but no one could prove they existed until over 50 years later. In 1974, Russell Hulse and Joseph Taylor found evidence of energy leaving a system of 2 orbiting pulsars. This was the first indirect proof of gravitational waves, and net them both a Nobel Prize for the discovery. The next logical step would be to directly detect the waves, and to do that, an entirely new method needed to be used. That new method ended up being LIGO, or the Laser Interferometer Gravitational Wave Observatory. This institution is composed of two giant interferometers in the United States. What is an interferometer, I hear you ask? At the most basic level, it's a device that uses light interference to make very precise measurements. To achieve this, a laser is sent down a tube where it is then split into two perpendicular channels. At the end of each channel is a mirror which sends the laser right back. The two beams then get rejoined and sent to a light detector. The version in LIGO is designed so that, under normal circumstances, the reflected light gets completely cancelled out when rejoined, thanks to destructive interference. However, if the length of the channel changes for any reason, the beams no longer cancel out, and some light makes it to the photodetector. The theory is that if a gravitational wave passes over the device while it is running, one arm will become slightly longer, while the other becomes slightly shorter. The inverse will then happen, and the process will repeat until the gravitational waves have passed over the instrument. A frequency of dimming and brightening light is produced, and that can be gleaned for information, like the audio clips we heard just a minute ago. That's the theory, anyway. Like everything in science, the process in reality isn't so simple. Because we, thankfully, don't have any massive objects orbiting in our neighborhood, these waves have to travel thousands upon thousands of light years to reach us, at which point they are incredibly weak. We're talking only can move stuff by 1/1000th the length of a nucleus levels of weak here. To compensate for this, LIGO has to be incredibly precise. When you're that sensitive, however, you create a lot of false positives, hence the cooperation of two interferometers. Only if both devices pick up a signal can it be confirmed that a gravitational wave was detected. Construction on LIGO started in the 90s, but it took almost 3 decades of improving technology and waiting before a gravitational wave was finally detected on September 14th, 2015. When it happened, everyone in physics collectively lost their minds. So now we know it took a long time to find one of these elusive undulations, but that still begs the question, why should we care about them? The simplest reason is that they provide additional proof for Einstein's theories, but we can go even further and argue that they could change the faces of astronomy and physics as we know them. See, much of the information we get about the universe is based on analyzing different forms of EMR. This works very well, but there are some problems that arise when you try studying something like two black holes merging, which, while incredibly significant, don't put off anything in the electromagnetic spectrum. Since gravitational waves work on a completely different level than light, they represent a whole new dimension of information we haven't been able to study before. They may be the key to understanding many uncertain questions in physics, like the true nature of gravity or the shape of the universe. Well, I guess I've done the bare minimum and answered the question I posed back at the beginning of this video. There is honestly so much cool stuff I simply didn't have enough time to get into, like all the unique tech that makes LIGO function, or the other gravitational wave interferometers around the world that are used in conjunction with it. While I still love my idea of gravitational waves being something you could surf on, the truth is certainly just as interesting and worth learning about if you ask me.